Hello, darling. Hello, my math angel. Math angel. Welcome back to Decaf-Math ASMR. And a very warm welcome if you are new here. How are you doing? I hope that you're doing all right. It's wonderful to have you join me here and right now. I want you to know that I appreciate you, even you, the silent watcher, the lurker, the ones that don't leave me comments, but leave me a thumbs up each and every video, or at least not a thumbs down, right? I appreciate you if you're here with me right here and right now. I hope that we can have a moment of peace and relaxation. If you need the rest, I encourage you to just close your eyes. We're just going to play around with a little bit of math, but there's absolutely nothing to stress about. Today we are going to take it nice and slowly here on our whiteboard. The last video was a bit more heavy on the math, and today we're just gonna play around a little bit. We're gonna take a look at two scenarios, for exponents that are a little bit wonky. So we've talked about exponents in the past and some exponent rules. Today we're going to look at the strange case of fractions in our exponent and negative numbers in our exponent. We're going to kind of look at the rules involved for those. So it doesn't matter though, don't worry. I'm just going to do couple of practice questions and that's it. We're just going to focus on the two key rules to know, which are really just definitions. If you happen to fall asleep, maybe you'll wake up knowing them, and if not, it really doesn't matter. We're going to get lots of practice around here. So why don't we just relax. Follow along with what seems interesting and let the rest just wash around you. Just let the math wash around you, okay? So let's start by briefly reviewing the basic idea of exponents, so the typical case, okay? So let's start with 2 to the power of 3. Okay, so we have a 2 in the base, 3 in the top, the exponent. 2 to the third power, 2 cubed, 2 raised to the third power. Okay, so this means that I take this base number, the 2, and multiply it by itself 3 times. 2 times 2 times 2. 2 times itself 3 times. Notice that that's not 2 times 3. It's not 2 times 3 times. It's 2 times itself 3 times. 2 times 2 times 2. 1, 2, 3 times. And what does that work out to be? Well, 2 times 2 is 4. 4 times 2 is 8. Excellent. That's all that there is to it. 2 to the third power is 8. 2 times itself 3 times is 8. So this can apply for 4, 5, 6, 10. Of course, it gets very, very large. So 3 to the 10th power would be 3 times 3 times 3 times 3 times 3, 6, 7, 8, 9, 10 times. That would be a very large number. But why don't we just try 3 to the 5? 3 times itself 5 times. 1, 2, 3, 4, 5. And we can just do this one at a time. 3 times 3 is 9, times 3 is 27, times 3 is something something, times 3 is something something. I think it's 81. But we have a calculator. Really, this is my excuse to make some calculator sounds anyway. So let's just write in, for a scientific calculator, you can write in 3 to the power 5, but let's do 3 times 3 times 3 times 3 times 3. That's 5 times. Can you see that? 3 times itself 5 times gives me 243, which is going to be 81 times 3. So that is what we get for 3 to the 5th power. There you go. That's it. So our base number times itself the number of exponent times. Now the wonky cases are what happens if we have a fraction in the exponent. What does it mean to multiply a number by itself a half number of times? That's actually really strange to think about. But we have a definition. So let's look at 16 to the 1/2 power. So again, it's 16 times itself, but now we have a half number of times, which is not half of 16. It's just this weird idea. Now, if I have a 1/2, by definition, this is going to be equal to the square root of 16. Do you remember square roots? It's kind of the thing that undoes our exponent, kind of, right? So if we don't have a number here, we're going to assume it's the square root, meaning what number times itself, or what number squared gives me 16, right? So what number times itself, like 3 squared, again in our classic situation, 3 squared would be 3 times itself twice. So what number times itself gives me 16? And in this case, that would be 4. Excellent. 4 times 4 is 16. Doing great. And that's it. That is it. And we're going to only look at positive square roots. By definition, note that, -4 squared, or -4 times -4 is 16. And I mean -4 in parentheses, right? So we're only going to look at the positive root here. So 16 to the 1/2 is the square root of 16. And that just happens to be 4. So this works for fractions like 1/3 or 1/7, right? So if we have third, it would be the cube root, which is the opposite of cubing. So instead of saying, 3 cubed is 27, the cube root of 27 is what number cubed gives me 27. Kind of undoes that. So let's look at that. Speaking of, 27 to the 1/3 means this thing times itself 1/3 times. That doesn't make sense. But by definition, this is going to be the cube root of 27. Which is just what number times itself 3 times, not 3 times the number, but what number times itself 3 times gives me 27, and that'll be 3. 3 times 3 is 9. 9 times 3 is 27, and you got it. So 3 would be our answer. Note here that we can have negative numbers in the base for cube roots because a negative number cubed would be negative, but for square root, we can't take the square root of a negative number in the real realm, so we don't really deal with those, okay? So just basically all of our regular rules for negative numbers and whatnot still apply for the base here, okay? But by definition, our 1/3 exponent is the cube root of whatever base. So our general rule is going to be a to the 1/n is the nth root of a. And so a to the 1/7 would be the 7th root of a. So what number times itself 7 times gives me a. That's that idea. Now, we don't always have the situation where the numerator of that fraction is 1, right? But this is the only rule that we really need combined with other exponent rules to get situations where the exponent or the numerator is not 1. So let's say we have 2/3. 2/3. So all we would need, again, the denominator tells us the root we're taking. So the bottom would tell me I'm taking the cube root, but if I have 2/3 instead, then I basically use another rule that we have for exponents, which is that if I break this up into 2 times 1/3, I can do this. If I have something to the power of something and that whole thing to the power of something else, then really the rule is that it's just equivalent to these two things multiplied. So 2 times 1/3 just as fractions multiplied to be 2/3. So I can break it up into something like this. Now I can do 27 squared. I can use a calculator or calculate that out. And I already know what to do with the 1/3 now. It's the cube root. So all this is still the cube root because of the denominator here, but the cube root of 27 squared. So if you are a pattern person, if you have a to the m over n, then it's the nth root of a to the m, if you want to write it like that without breaking it down like this. Or alternatively, you can actually flip-flop this because 1/3 times 2 is still 2/3. And so I still have the same rule. Stuff to the power of stuff to the power of stuff means you can multiply the two exponents. 1/3 times 2 is still 2/3. So I can go ahead and take the cube root of 27 first, which we said was 3. We got it before. So all we would really have to do is square our answer to get 9. So in this particular case, we can actually go ahead and take the cube root first and then square it. Just be careful of situations where you might have negatives and just deal with those accordingly. But in general, you can just follow this trick here. The a to the m over n is the nth root. So the denominator always tells you the root, and then just raise your thing to the power of the numerator if you want to deal with it that way. Sometimes, like in this case, it's just easier to take the cube root first, so you just go ahead and do that, okay? So that's it. We have our 1 over n situation, and therefore m over n as well. Very good. We can get more practice, and we can mix and match different exponent rules as well moving forward, but for now, we're taking it nice and slowly and introducing these rules. So now let's just do a negative exponent case. So let's look at the negative exponent case. Let's say we have 5 to the negative 2. 5 to the negative 2. So now I feel like this is even weirder because we're thinking about 5 multiplied by itself negative twice. That's so odd, right? 5 times itself, so it's not 5 times negative 2. It's 5 times itself negative 2 times. That doesn't make sense. Sounds like we'll need a rule. We have a rule, and that is if we have a negative exponent, we just flip it to be a reciprocal. So we just do 1 over 5 to the positive 2. So we just make that negative down in the bottom, and we just keep a 1 over 5 squared. So 5 squared is going to be 5 times itself twice. So 5 times 5 is 25. So 1 over 25 is our answer. But as far as a rule goes, it's really just a to the negative 1 is equal to 1 over a. And then from here, we can do the same thing that we did with the exponents, breaking it up to have, negative 2 is negative 1 times 2. So we could think of it like this, right? If a to the stuff means that I can multiply the two exponents, and negative 1 times 2 is negative 2, then I can just do this rule, 1/5 squared. From there we know it's 1/5 times itself twice, so 1/5 times 1/5 is 1/25, or we can do it the other way. We can do 5 squared to the negative 1. Because 2 times negative 1 is still negative 2. And so we can do 5 squared is 25. And again, directly applying this, 1 over 25. So you can actually play around with this. In general, you could just say a to the negative n is 1 over a to the n. But it's cool to just break down to the baseline pieces. And since we've already talked about other exponent rules, we can just mix and match and combine them, and it's cool to just break it down to the basic building blocks. So that's what I'm trying to focus on here. But as you practice, if you see 5 to the negative 2, you might not need to just go through all this. You can just do 1 over 5 squared. So we'll just do one more. 3 to the negative 3. We have a negative exponent, so we do 1 over, and then just 3 to the 3. And here's our regular exponents. 3 times itself, 3 times 3 is 9, times 3 is 27. So we have 1 over 27. And that's it. That is it. So we have our negative exponents, and we have fraction exponents now, and we have irregular exponents, and we have a bunch of exponent rules. So now we can just mix and match. Imagine if you have, a negative number raised to, I don't know, like a negative fraction exponent. We'd have to be careful with roots of negative numbers, but it'd be pretty cool to mess around with. You might have just regular exponents, but then raised to, I don't know, negative and fractions, and I don't know, whatever. You can mix and match them. And so we can do some fun problems with that. And what gets interesting is with negative exponents, we have a reciprocal like this, but it applies to a situation if your base is a fraction as well. You can still take the reciprocal of a fraction by flip-flopping the numerator and the denominator. It's not always just 1 over. It's 1 over if we just have like a 5. But in general, if you have 2/3 to the negative 1, it would be 3 over 2. Flip-flop, flip-flop. And that's it. So we can definitely have fun going over more practice questions or just random problems. Now we can put things together. But for now, I wanted to just take our time and introduce the idea of a fractional exponent and a negative exponent, just because it seemed kind of weird. But I hope that you enjoyed that. If you are asleep already, sweet, sweet, sweet dreams. If you are getting drowsy, I encourage you to just snuggle up and allow yourself to drift off. If you have to continue the rest of your day, I wish you a very nice rest of your day, evening, night, whatever time it is for you. I will see you around for more math very, very soon. Please take good care